Hey y'all. Today we're going to be looking at a really critical new concept, and that's something known as Le Chatelier. And in chemistry, Le Chatelier really comes down to one thing: comparing Q to K. In order to do this, we're going to need to get started by looking at how to find Q, compare it to K, and then what that actually means. Let's get started. For this video, it's going to be really important to remember that both Q and K are found using the same basic ratio of products over reactants, our mass action law. And when Q is equal to K, we are in a system that is at equilibrium. That means when Q is not equal to K, we're not at equilibrium. And the focus of today is, number one, figuring out how we can change our Q compared to K, and how we can predict which direction a reaction is going to shift as a result of Q not being equal to K. Because remember, we want to reach equilibrium, and we can reach equilibrium in either the forward direction or the reverse direction. The basic premise of Le Chatelier's principle is that when a system that is at equilibrium is perturbed in some way, that system will respond by returning back to equilibrium. That equilibrium position is potentially going to be different than the one that it was initially. The whole idea of Le Chatelier comes back to comparing Q to K. When Q is greater than K, we think back to our products over reactants. When Q is greater than K, then we would have more products than compared to at equilibrium. As a result, the reverse reaction goes faster than the forward, and as a result, the entire reaction shifts to the left, towards our reactants. When Q is less than K, then we think of that mass action law again. The reactants would be too large compared to the products relative to where we'd be at equilibrium. The forward reaction would be faster than the reverse, and the net movement or the shift in the reaction would be in the forward direction, creating more products until, again, we reach equilibrium. So when Q is not equal to K, the entire system will shift or proceed in the direction necessary to return our equilibrium system to a state of equilibrium. There is a quick memorization trick that you can use to remember which direction a reaction is going to proceed. Admittedly, I don't love it because it kind of loses the conceptual idea of why a reaction is going to shift to the left or the right. But if you're desperate for a trick, here's the trick for you. If we write K and Q alphabetically, that means K comes first, and K is greater than Q, then the arrow is going to point to the right. As a result, the entire reaction shifts to the right. If K is less than Q, the arrow shifts to the left. And as a result, the entire reaction will shift to the left to reach equilibrium. Again, I don't love this trick because it is more memorization-y and less conceptual understanding. However, like I said, sometimes it's nice to have a memorization kind of trick in your back pocket to use if you need it. There are a number of different things that count as stressors within the Le Chatelier realm. Specifically, today we're going to focus on the ones that affect the Q value. This means they change either the concentration or pressure of reactants or products. So a couple of examples of these include adding a reactant or a product directly, removing a reactant or product directly, changing the volume, changing the pressure. Those are types of stressors that can impact the Q value compared to K and cause the entire equilibrium position to shift. Additionally, there is another stressor, changing temperature. However, changing temperature doesn't actually change the Q value. It changes the K value. It turns it into a new K value. We're going to talk about how that happens in a later video. The first stressor we're going to look at is changing the amount of reactants or products. If we directly add a reactant, so we increase the concentration or the pressure of a reactant, that is going to decrease the Q value because it increases the denominator, and it's going to cause Q to become less than K. This shifts the reaction in the forward direction. We can think about this like kinetics too. If we add a reactant, it increases the rate of the forward direction because collisions of the forward direction are going to happen more frequently. They're going to be more effective collisions as a result. That's going to increase the rate of that direction. So the forward becomes faster than the reverse, and the entire reaction shifts forward. If we remove a reactant, the opposite happens. If we remove a reactant, we are going to end up decreasing the rate of the forward reaction. And by decreasing the rate of the forward reaction, it's going to show an overall net movement in the reverse, because now the forward is slower than the reverse. If you think about this in Q versus K, we decrease the amount of a reactant. We're going to increase the Q value because we've made the denominator smaller. And that's going to, again, shift that reaction towards our reactants. The same thing can happen with the products. Increasing the amount of a product is going to shift the reaction in the reverse direction. Decreasing the amount of reactant or of the product is going to shift the reaction in the forward direction. We can think of it in terms of kinetics, that's conceptual, but we always have to describe it in the Q versus K framework. Again, if Q is greater than K, what's going to happen is the entire reaction is going to shift in the reverse direction. If Q is less than K, the entire reaction is going to shift in the forward direction. The next perturbation or stress that we're going to look at is changing the volume, and this affects both gases and aqueous solutions. Let's start with gases. If we increase the volume of a container that gases are in, we're going to favor the side of the reaction with more moles of gas. And that's because the Q value is going to change. This is as a result of the fact that we have, let's say, 2 moles of gaseous things in our products. Therefore, that change in volume is going to be affected twice as much because you're doubling the effect, right? You're multiplying half by half or double by double. And so our Q is going to change as a result. So let me repeat how this works. If we increase the volume of a container of gases, we're going to favor the side of the reaction with more moles of stuff, more moles of gaseous stuff. If we decrease the volume of the container, we go in the opposite direction. We favor the side of the reaction with fewer moles of gaseous stuff. For concentration, as we dilute an overall aqueous solution, we favor the side of the reaction with more moles of aqueous stuff. And if we were to concentrate a solution, we'd go in the opposite direction. We would favor the side with fewer moles of aqueous stuff. Again, this all comes back to Q versus K. As the Q changes, we're going to shift back till we reach K again. And depending on which direction we are shifting, it really does depend on how many moles of things are being affected. Let's do a practice problem to see this in action. Here I've got a chemical reaction and I want to remove the hydrogen molecules from this reaction vessel. So maybe the hydrogen molecules escape. I don't know. But either way, there's going to be less hydrogen molecules present. What is that going to do to the overall reaction? Well, let's think about it. Hydrogen here is a product. And as a result, as we remove it, what we're doing is we're decreasing the Q value compared to K. Remember, products over reactants. So Q becomes smaller than K. When Q is smaller than K, we favor the forward reaction direction. So the entire reaction will shift to the right. Now keep this in mind, and this is really important. We can also think about this in kinetics. By removing hydrogen, what's happening is we're reducing the rate of that reverse reaction. The forward reaction hasn't changed. It's still going the same rate it was. Those collisions are still happening as frequently as they were. So what happens is we reduce the rate of the reverse. The forward now is going faster. So the net shift in the reaction, the net preceding reaction is going to be in the forward direction. Let's take another example here. Now, this is the Haber process where we take gaseous hydrogen and nitrogen and combine them together to make ammonia, NH3. When we look at this, if we were to decrease the volume of the vessel, what would happen to the equilibrium system? The answer is it would cause the reaction to shift to the right, towards the ammonia. And the reason is because a decrease in the volume is going to favor the side of the reaction that has fewer moles of gas. The left side of this reaction has 4 moles of gas. The right side of this reaction has 2 moles of gas. Therefore, as we decrease the volume, our Q becomes less than K, and we will shift to the whole reaction to the right. Now, one thing to be aware of, and this is really important when it comes down to how we process these types of problems, is when we first cut the volume in half, all of the pressures double, all of them. And then what's going to happen is the reaction is going to shift to the right. So the pressures of the hydrogen and nitrogen are going to come down. The pressure of the ammonia is going to go up. But one thing to be aware of is the hydrogen and nitrogen pressures will never actually get back to where they were before we cut the volume in half. It's just an interesting tidbit. This next practice problem is kind of fun. It involves complex ions. In fact, this complex ion is probably the first one you've seen this year. A complex ion is simply an ion that is formed out of a group of things that might by themselves not be ionic. So for instance, on the left side of this reaction, we've got a cobalt complex ion where it's hydrated with water molecules, 6 of them specifically, and has a total charge of +2. So this is a complex ion. Complex ions are used a lot in chemistry equilibrium because they do a really nice job of showing chemical shifts because they have colors to them in a lot of cases. In this case, that cobalt complex ion is red. On the other side of this equilibrium system, what we see is a cobalt chloride ion that is blue. And so we actually can identify where we are in our equilibrium based just off of the color of the solution. If the color of the solution is red, then I know that my reactant is favored. If the color of my solution is blue, then I know my product is favored. So let's say we start at equilibrium, right, where we're right in the middle. What if I added silver nitrate to this solution? Let's think about what that might do. Well, silver is a really interesting reaction here because the silver ion will precipitate out the chlorine ions. And as those chloride ions precipitate out, they form silver chloride, a solid. Solids aren't existing in our equilibrium system. So what I'm doing with my mass action is I'm actually removing my chloride ion. That's going to cause the entire reaction to shift to the left, turning it red. Because as we shift to the left, it's due to the fact that my Q is going to be greater than my K because I've reduced the amount of a reactant, right? I've made a reactant smaller, makes my Q bigger, makes my entire reaction shift to the left. Therefore, my entire solution would turn red just by removing a reactant, chloride ions, from the reaction using precipitation of something that wasn't even in the reaction, the silver chloride, or the silver nitrate, should I say. So again, one of the ways to shift a reaction is to add anything, a reactant or a product, but one of the ways is removing. And this is a really clever way to remove a reactant or a product through the formation of a solid precipitate. All right, so that wraps up today's video. Let's recap. Today we focused on how Q and K can be compared to predict the reaction direction and how a reaction will proceed when it's not at equilibrium. If Q is less than K, we shift the reaction to proceed towards the products. If Q is greater than K, the reaction will proceed towards the reactants. We also talked about some of the different perturbations that we can do to stress a system to cause Q to not be equal to K. Things like adding products, removing products, adding reactants or removing reactants, changing volumes, changing dilutions. All of these things can be causing the Q to vary. Remember, if we change the temperature, we're not changing Q. We're just changing K from one K to another. And in a future video, we're going to cover exactly how that happens. Today's video was written, directed, edited, and produced by Anthony Yang and Jason Guo. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one. No, God bless it. I love Anthony Yang and Jason Guo.